Hello everyone. So for the first lab today, we are going to be talking about what is Kirchhoff's laws. When I say Kirchhoff's laws, there are two laws of Kirchhoff. One is Kirchhoff's current law, another one is Kirchhoff's voltage law. So before I move on to that, I have to talk about certain circuit combinations. That's the first thing. And then afterwards, how we can actually verify Kirchhoff's current law and how we can verify the other one, which is Kirchhoff's voltage law. I am going to talk about that. So I guess most of you are new to this concept of the series and, in total the circuits. So when I say about two circuit elements, whether they are in series or parallel, this is something you have to know, in which combination circuit elements are. That's the one thing. Another one is you have to be able to distinguish them properly. This is something you have to be very clear about. Otherwise you wouldn't know what you are measuring and what you are going to do in future, because since this is a very basic foundation, so I want to make sure that all of you know it. All right, so the first thing first, so we know that whenever there are two circuit elements, and when they're side by side and there are no other circuit elements in between them, I mean, when I talk about in between them, that means node, when they have a common node. So see, what I am talking about is, you see, just consider this number one circuit for example. Okay, as you can see, I am supplying the power from here. There is one resistor over here, another one over here, another one over here. You need to know whether this is in series or it's in parallel. So when two nodes are, there are no circuit elements between them, then you can say these two nodes are, the same. And whenever two nodes of two circuit elements are same, then you can say they are in parallel. What am I saying actually? What does this mean? So that means that, you see, this is a 10 volt power supply, all right, and there is a 1 kilo ohm resistor. For example, let's consider these two are not here. Over here, if there was a resistor, then this and this would not be the same node, right? Because they would be separated by a circuit element, whether it could be, and when I say circuit element, it could be a resistor or inductor or capacitor. So when there is no circuit element in between them, that means this node is same. Similarly, as I said, forget about these two elements. So for this one also, we can see that this node and this node are same. So since they are the same over here, this is one node 1, and this is another one, which is node 2. So since node 1 and node 2 are same of these two circuit elements, so we can say that this one and this one, this both are in parallel. Similarly, you can see 2K, this node is, this is one node, this is one node. Similarly, this is one node in between these two, and this is one node. What does that mean? That means this 1K is parallel with everything. This 2K is parallel with this one, and this one. This 3K is parallel with this one, and this one. Okay, so now when I say if there is a circuit element in between them, then what would the circuit would look like? So now take a look at circuit number 2. So you can see there's a power being supplied from here. So for example, there is a resistor over here, another one over here, and another one over here. But even though this one is okay for these two nodes, but these two nodes are not the same. Why? Because there is a resistor in between them. So since these two nodes are not the same, that means this 2K is not in parallel with this one. But is 1K parallel with 2K? Yes, because this node and this node, it's the same node. This node and this node is the same node. Remember, so 2 ends represents two nodes. So when two nodes of two different circuit elements don't have any circuit elements between them, then they are in parallel. Now, is 1K and 1K, in parallel? This node is similar for this two, but there is a circuit element in between two. So this is not actually, this one and this one is not in parallel combination. So how do you actually figure out what is the equivalent resistance of this circuit? So I didn't draw it because I have to see. So whenever you have a circuit combination like this, okay, see this one, this one, this one. So the end of this resistor connects with the start of this resistor, and the end of this resistor connects with the start of this resistor. So if this is the case, that means these three resistors are in series, and when they are in series, the value of them adds up. And now for this circuit, I talked about these three resistors are in parallel. So since they are in parallel, so this is the notation of how you write the parallel circuit. So basically, what would be the total resistance of these three resistances? It would be 1 over 1k plus 1 over 2k plus 1 over 3k inverse. So when you put the values in the formula, that's how you can find out what is the equivalent resistance of this circuit, right? And another thing, what would be the equivalent resistance of this circuit then? If you have understood what I have just talked about, I guess you would be able to figure out what is the equivalent resistance of this circuit. Even though we are going to be talking about what is Kirchhoff's current law and what is Kirchhoff's voltage law, but still I believe this is a very important concept. So this circuit is something that I want to see you guys solve, which is I want to know what is the equivalent resistance of this circuit. This is something you have to add to whatever we are going to learn today. All right, so now for Kirchhoff's current law, what I'm going to do is take this circuit as an example. So let's say this is circuit 1. So for circuit 1, you can see like 1 kilo ohms, 2 kilo ohms, and 3 kilo ohms. These resistances are in parallel with the load. That means, sorry, not the load, the voltage source, right? So the voltage is being supplied, and then it's actually based on the load, it's generating a certain amount of current. I don't know what is the amount of current is being generated, but let's say it's I. So this I current is coming to this node, and then from here the current is being divided into two portions, which is I2 and I1, right? And then this current I1 comes over to this node. Let's say this is node number 2. Then this current is being divided into I3 and I4, right? So that means the total current is I2, which is this one, I3, and then sorry, I3 is this one, and this is I4, right? So that's the total current. Now, what Kirchhoff's current law specifically says is that for a certain node, the amount of current entering and the amount of current exiting, the algebraic sum of that has to be 0. Like, let's take this node for an example. This is node number 1. So at node number 1, what is the current entering? I1. So since it's entering, I will consider this as positive. You can consider this as negative as well, okay? But then you have to consider the other ones exiting as the of the opposite sign of what you're considering for this one. So I just considered this one positive. And then what is the current exiting? Not only I2 is exiting, but also I1 is exiting as well. So since these two are exiting currents, I would write I1 as minus, then I2 as minus, and then I would make it equals to 0. So if you actually measured the values and if you actually see, then this equation would definitely actually become 0. So that's what Kirchhoff's current law states, okay? And then what about the Kirchhoff's voltage law? So Kirchhoff's voltage law states that if you supply a voltage, in a closed loop circuit, so the voltage drops across this, if you sum all of them up, then it would be equal to 5 volt, or in another word, the algebraic sum of the voltage drops across all of these resistors. And if you write the equation for it, it's going to be 0, which is like this is 5 volt, so supplied voltage, then the drops are going to be of negative signs. So you just it's just like Kirchhoff's current law, right? So you just place those values and make it equals to 0, and that's how it's going to be and that's how you can actually verify like what's Kirchhoff's voltage law is. All right, so over here you can see that I have 1 kilo ohm, 2 kilo ohm, and 3 kilo ohm resistors in series. So what you can do is, the voltage being supplied, the equivalent resistance, so you divide that, and what's the current you are gonna get? You just find that out first. And you also know what is the Ohm's law, right? So Ohm's law is V is equals to IR. So that's how you actually find out the current. So when you actually find out the current and you actually know the resistance, so current, you see same amount of current is actually passing through. These all are in series. So when they are in series, same amount of current passes through, right? Like see over here, I just divided up this circuit. Like 2K could be written by, series combination of 1K and another 1K. Similarly for 3K, it could be 1K, 1K, 1K. So if that's the case, then what happens is, like the current that's coming over here, it's going through this resistance. That is coming over here, the same current passes through this two, and the current that's coming over here, the same amount of current passes through these elements. So that's the same for, same current passes through the series elements. So over here, it's the same. It's not different, right? It's going to be the same current passing through 1K, 2K, and 3K. So when I know the entire current, so current times the value of the resistance, then I know actually what's the voltage is. That's actually what you can say as a calculated voltage, okay? And the measurement voltages, we are going to be doing, the measurements with the help of, the Labrador kit, the Labrador device. Basically, you can do it with the help of a multimeter as well if you are well equipped, but this is a very complicated portion. Multimeter use would make it very easy, just to make sure you guys understood Lab 0 and how to measure currents with the help of, Labrador. I'm gonna be using, the Labrador to measure the currents across, what should I say? I'll be using Labrador just for measuring the KCL values, the current values that are passing through, this resistor, this and this. But for voltage, drops calculation, I'm just gonna use the multimeter to measure what's the voltage across this are gonna be. That way it would be very easier. It's a long lab. I want to make sure like all of you can just complete it. The main focus over here is like learning the whole thing. Okay, so that's how you actually can so when the calculated and measured values are equal, that's how you can actually verify, okay, that what you're supposed to get. And so that would be so this is the main gist. And besides, like I talked about, I am going to be giving you two circuits, and I want to know for this circuit, like I talked about, I want to know what is the equivalent resistance of this circuit. And then I'm gonna give an additional circuit and ask you, like, what is going to be the current through that circuit. Like I will just when I am going to be creating this circuit setup manual for this lab, over there I am going to mention it. And this is something I am doing to make sure that you guys are learning, because for the Lab 0, what I did a thorough manual, and then if you followed that, your lab would have been totally done. So the concept that I discussed about series resistance and parallel resistance, and how you can actually measure the equivalent resistance of a circuit, just to make sure if you have understood the concept of the equivalent resistance as well as how the current actually passes through it, like I discussed. So I will add this circuit and an additional circuit just to see like if you guys have learned it. Okay, I'm gonna move on to the KCL circuit setup and then carry on from there. All right, so before constructing the circuit, a lot of you have asked me the question during the Lab 0, which is how can you actually know which one is 1 kilo ohm resistor or which one is 100 ohm resistor. Could you please tell me the color code? Guys, let me just assure you, nobody memorizes what is the actual value of a certain resistance based on the color code. Okay, what you have to do is you have to measure with the help of the multimeter that you have. So how can you do that? All right, so I'm gonna just give you one simple demonstration, and from which you can actually figure out what is the value of the resistances, and I guess from now on you wouldn't find it difficult. So if you keep on doing this, for a couple of times, you would be just fluent on, about this. So just don't worry about it, just follow the instruction and then just carry on from there. Okay, so I know that for constructing today's circuit, let's say for KCL, I'm gonna need one 1 kilo ohm resistor, one 2 kilo ohm resistor, one 3 kilo ohm resistor. And if you remember, like while using the Labrador, if I want to measure what is the amount of current that's passing through 1 kilo ohm, with the help of the oscilloscope, or the using the oscilloscopes that's in Labrador, I have to make sure that 10% of the resistance is connected across the channels. That's how you actually measured it, right, in the first lab. So today you have to do the same thing. So for example, if you want to measure currents across 1 kilo ohm resistor, then you have to connect the duplicate channels of the oscilloscope in a way that it is also in a parallel combination with the 10% of the resistor across which you are measuring the current. You have to, you need to have that. Okay, so what I am going to do is like first measure one resistance value. Let's say that I am looking for something around 2k. Now where do I set this one? Okay, so for example, this this values actually represents, like you see, ohms. That means these are representations of where the maximum value of the resistance a certain point can count to. For example, like if over here it's mentioned 200, that means if I try to measure a resistance and if the value is over 200, I'm not going to be able to see the value. So in order to see values above 200, I have to set it to 2000. That is 2000 is the 2000 ohm is the value of the resistor, that it can read. If I point this probe over here, it's 20k, over here it's 200k, over here is 2000k. All right, for example, like I just want to take this resistor. I don't know what's the value of this one, so I'll just put it to 200k, and then I'm just gonna I'll just place it somewhere so that it doesn't move, and then I'm gonna measure. I'm gonna just do this like this, and you can see it doesn't show any value, like just blank one. That means this resistance value is above 200. So what I'm gonna do is turn to 2000. Now if I place it, still it's 1. Now when I moved it to, when I move the limit upper, then you can see it gives me 3.23. That means 3.23 k. K means like kilo ohms. Okay, so that means 3.23 kilo ohms is the value of the resistance. So that's how you actually measure like what is the value of a certain resistance. Okay, similarly you have to find out what are the resistances you need, and you have to find it out by measuring it with the help of multimeter. Yeah, you can obviously look at the color code, but that's not how we do it, because you cannot actually memorize the value of a resistance. You can never keep it in mind by just memorizing the color codes. Okay, so that's my recommendation. All right, so the circuit setup. Okay, so like I said before, I'm going to be supplying 10 volts. So over here I'm gonna have 1 kilo ohm resistor, 2 kilo ohm and 3 kilo ohms in parallel, right? So for 2 kilo ohm, like I didn't get exactly 2 kilo ohm, I got somewhere around 2.24 kilo ohm resistor, and then it's the similar case over here, like 3.34 or something like that, but that's totally okay. Like I measured it, so I know like what to expect. Okay, so first, before supplying 10 volt, I want to make sure like I connected rest of the portions properly. So over here what I did was I just had these things like connected, which is, you can see there is only one common node. I just put one one node of the 3k over here, 1k over here, and 2k over here. The reason why I did this is because, like, the resistors are properly placed, so I just I could, like, connect it manually. So, like, when I'm trying to measure the currents across this, so I would have to move the resistors. So just for the fact that I don't have to do so, I just did it like this. The reason why I did it, you can see, like, just for my convenience. Okay, so in order to connect these nodes, I first have to, so 2 kilo ohms node is over here. So I'm gonna place one wire, right? And then place it in a way, I'm sorry, and then connect it over here. So I just connected this end to this end. Then now I'm going to connect this end to this end, which would basically mean these all ends are connected, and the parallel circuit would be complete. So this was 1K over here. Like if you can see properly, this was the end of 1K. So I'll just grab this and then connect it over here. So now all the nodes are connected, and that means this entire circuit, I connected this, now I have to connect this. Okay, so that means I will have to connect that, just this end with this end. Over here, just like this. I just connected the negative one over here, the positive one over here, positive one over here, negative one over here. Okay, now I have to first make sure I'm supplying 10 volt of power to this. Now we have to first verify Kirchhoff's current law, right? That means that at this node, the amount of current entering has to be equal to the amount of currents that is exiting. So I will measure what's the current exiting from here, coming over here, what's the current going over here, similarly what's the current going over here, and what's the current going over here. So if you remember, in order to measure this circuits, what is the current passing through here, I have to arrange it in a way so that so now that I'm going to be measuring what's the current that's passing through 1 kilo ohm of resistor, what I did was, if you remember, like I connected these three nodes together in this circuit, right? So now I have to make a discontinuity over here. That means these two will stay connected. I'll just disconnect this one, which is over here for my circuit. I'll just disconnect that one. Now that portion will go to oscilloscope channel 1, and this portion will go to oscilloscope channel 2, like the duplicate channel. Okay, so what I'm going to do is I'm going to connect the ground with the oscilloscope channel 2 and the other end of the resistor with the oscilloscope channel 1. Right, so now that I did this, if you remember, like when I connect this one, not only I have to do this, but also I will have to connect 10% of the resistance across which I'm measuring the current of. 10% of the resistance value has to be connected in parallel with the oscilloscope channel 1 and 2, right? If you remember, so I have 1K over here. What I'm going to do is, like, take the duplicate channel of oscilloscope 1, and then if you remember, so what I did was, over here I made 100 ohm connection, over here I made 100 ohm connection. When I add all of this together, it would be like around 200 ohm, which I would require for measuring the current when I'm trying to measure it through 2.2 kilo ohms. And for 3.3 kilo ohms, what I did was, like, you could add 6 of the 50 ohms in series, and then have 300 ohms. Or what I did was I had a resistor of 670 ohms. So when you have two similar resistances connected in parallel, then their value actually becomes half. And what is the formula? The formula is 1 over R is equals to 1 over R1 plus 1 over R2. This R is actually R total. That means R total is equals to 1 over R1 plus 1 over R2 inverse, right? So if you had two similar values, then it would just reduce to half. So I have two 670 ohms. So this 670 ohms divided by 2, that would be around 335 ohms. So these are the values I would require. I just prepared it just for this case. So now since I'm calculating for 1 kilo ohm, what I'm going to do is like connect 10% of the 1 kilo ohm value across the oscilloscope channel 1 and 2, right? So I took a duplicate channel out of oscilloscope 1, I connected it over here, and then I'm going to take another duplicate channel of oscilloscope 2 and then connect it over here. So these two resistances that you are seeing in series, this makes up 100 ohm, okay? And now if you have seen, like I still haven't connected my power, so I am going to connect my power, and then I am going to move over to the screen. All right, so now that I'm on screen, what I did was first adjusted the power over here, which is like I made sure that 10-volt power is being supplied. Then I just locked it to make sure, and then I unchecked the oscilloscope channels 1 and 2. I checked multimeter option, then I switched to current, and then I put the value of the resistance over here, which I connected across the oscilloscope channel 1 and 2. And after I entered that value, this is the maximum and minimum value I am getting, okay? And then I'm gonna do the same for 2.2 kilo ohms, and then the same for 3.3 kilo ohms. So now that I have calculated one current through 1.1 kilo ohms, now I have to do what is the same for 2.2 kilo ohms, okay? So I had a discontinuity over here. So first what I'm going to do is discontinue over here and connect this one. So I'll just discontinue. Taking the oscilloscope channel 1 out of that, then connecting it over here, which is here, and connecting 1 kilo ohms over here. And now what I'm going to do is, you see I had 250 ohms over here, 250 ohms over here, so that means it would sum up. So separately it's 100 ohms, separately it's 100 ohms. So I'm just gonna make a connection between two and make a total of 200 ohms. And if I add another wire to it, this would become 200 ohm, which is around 10% of the 2.2 kilo ohms of resistance across through which I want to measure like what amount of current it passing, right? So now over to the screen. Right, so after the circuit connection, I came over here, and what I did was I just changed the series resistance, because like I used 2.2 kilo ohms, that is the resistance across which I will be measuring the currents. So you have already seen the circuit combination. So what I just did was change the value of the series resistances, which is around 10%, but not exactly 10%. So 180, it becomes 186 ohms, which was supposed to be 2.2 kilo ohms, but at least 186 ohms That's closer, so I just put it there. And if you once you do, you are gonna get the value across, the amount of current that's actually passing through 2.2 kilo ohms. So note this one down. You have to take a screenshot, like I said before. That's the same thing you have to do for 1 kilo ohms. You're gonna do the same for 2.2 and 3.2 as well. So this is for 2.2. That I'm done for 2.2 kilo ohms. I'm gonna do the same for 3.3 kilo ohms. Okay, so this was the circuit setup for 2.2 kilo ohms. What I'm going to do is first take off the duplicate channels. Okay, and then the channel 1 and 2 as well. Now this was the equivalent resistance for 2.2 kilo ohms. Like I said, I connected two 670 ohms in parallel to make it around 335 ohms, which is like around 10% of the value of the resistance across which we are going to be measuring the amount of current passing through, right? So I had 1.1 and 3.3's bottom node connected, so I'm gonna have to disconnect that. Now I'm going to connect 1.1 kilo ohms bottom node and the 2.2 kilo ohms bottom node together, and then make this one discontinue. So 1.1 kilo ohm and then 2.2 kilo ohms, those two are connected. Number 3 is disconnected. Oscilloscope channel 1, so see, for my circuit I connected the ground across this one, so I'll have to take that one off too, right? Now I connected oscilloscope channel 1. You have to be very careful because you are dealing with 10 volt of power, right? So that's channel 1, and then the channel 2 would go to ground. Now for the series resistance, oscilloscope channel 1 duplicate, oscilloscope channel 2 duplicate. Okay, now that's what I did. If you were not able to see, this was the parallel combination that I talked about. I'm sorry about that. So oscilloscope channel 1 once again came over here, oscilloscope channel 2 over here, two 670 ohm resistors connected in parallel to make the value half, which is 335 ohms, and this is the value of the series resistance I'm going to be using to measure the current which is passing across 3.3 kilo ohms. And if you remember, like the ground was connected over here, so I just discontinued it. That's what you have to do in order to measure the currents, otherwise it would be short and the current wouldn't be proper. Now I'll go over to the screen. All right, so after the circuit setup for measuring the current passing through 3.3 kilo ohms and the setting up the oscilloscope channels properly, I came over to the screen. So as you can see, I already had the series resistance measured, which was 335 ohms, and this value is 10% of the value of the resistor across which we want to measure what amount of current is passing through. So you can see it's ranging from 2.82 to 3.15. So this is the value. I'm gonna pause, take a screenshot of this, and later on I'm gonna use it to verify my results. Now for the Kirchhoff's voltage law, what I'm going to be doing is like measuring the voltages across the resistances of the circuit to see if it sums up to the voltage that we are supplying. So the voltage I'm supplying is 10 volt. This is my circuit combination that I put over here, right? So forget about this ones. So this is the actual circuit like I'm going to be, considering. So what I did was first I pointed at the marker of the multimeter towards 20 volt of DC voltage, because we are supplying around 10 volt. How maximum could it be? Like around 11. So I just set it to 20. That's the maximum value it can reach. So if I put the probes like this, you can actually see the value of the voltage across 1.1K, which is 1.5 volt. Then across 2.2K, it's 3.3, 1.5, 3.3, and 4.9. So 1.5, 3.3, and 4.9, right? I just want to make sure about the last one. Yeah, 4.9. So I'll just add all of those up. So 1.5 and 3.3 is 4.8. So 4.8 and 4.9 is around 9.7, right? Which is equivalent to 10 volt. Okay, it's not going to be perfect all the time because electrical components are not that perfect. Okay, so 9.7 volt approximate to 10 volts. So how you can, so since I'm using the multimeter, you might ask a question that how you want to include these readings in your lab report. So what I would recommend you to do is take a video like this, and then the point where it reads the value, so you just pause it, take a screenshot of that, and then that's how you can have 3 different screenshots of the voltages you are reading, you are reading across these resistances, and that's how you can add that to the lab report. So basically that concludes my lecture for this lab, where KCL states that the algebraic sum of the current entering any nodes in a circuit is equals to 0, and for Kirchhoff's voltage law, it is going to be the algebraic sum of the voltages around any closed path in a circuit is equals to 0. That means whatever the the amount of voltages is being dropped over here, in another word, it's going to be equal to 10 volt. Okay, so I'm gonna move on to the question answer session now.